Okay, let's just come back here. Okay, last time we introduced the concept of the hypothesis test. So remember, the idea is if we have our hypothesis, whatever that is, our null hypothesis, we're trying to see if we have our enough evidence to show that it is not true. Okay, even though at the end of the day, we can only believe whether it's true or not true because we have always got the errors to consider. We only, however, but we are allowing ourselves a merely 5% or 1%, a small proportion, small value of alpha that we will reject our null hypothesis wrongly. Okay, this is what we call the significance level. This is what we call significance level. Okay, we're trying to see if our experiment result is an unlikely event if H0 should be true. Okay, we have with our little example of my silly little coin trying to show that this is fair. How would you perform an experiment? Okay, we have a hypothesis whether my coin is fair, like the probability of getting hit is exactly 0.5. Okay, then we use our alpha, our significance level here to determine a critical region. Okay, determine a critical region. We can't have our number of hits too many of them. We can't have too many of them hits or too few of them hits. If we were to toss this coin, I don't know, like 20 times or 50 times or 100 times, we use this alpha value to write down a critical values so that when eventually when we perform our experiment at the end, like having the number of hits thrown, then we can see, okay, it belongs to a critical region, or no, it doesn't belong to a critical region, and therefore we reject or not to reject our H0. Okay, that's it really about our significance level. Okay, but it's sometimes very easily misunderstood. Okay, the thing is, we're looking whether this alpha or this is effectively okay. We're assuming our null hypothesis to be true. How likely it is to obtain a result? Okay, so if it is an unlikely event, so small a value that it is unlikely to happen, therefore we say it's probably something wrong with our hypothesis. The fact that H0 is true is probably not the case. But in reality, what we want is really, given the results that we're having, given the exact experiment result that we're having, the experiment data and all that, what is the chance, what is the probability that H0 is true? So we always have this sort of problems of false positive and false negatives that we discussed earlier, well, with the earlier chapters when we had our medical tests. Really, any test has this problem. The test result and the truth may not be the same thing. Yeah. Okay, and we talked about how to do these calculations earlier. We're assuming a null hypothesis to be true, etc. So, and we're using alpha to do this. So, when my coin, it'll be assuming p equals 0.5 as my null hypothesis. So when it is not true, then it will be like it is not fair. Then p not equal to 0.5. Then, okay. Most of the time, or almost always, you should have your null hypothesis, the one with the equal sign there. Okay, because this is the one that you're assuming to be true, and we're using this in our calculations, assuming p equals 0.5, and see how unlikely things would happen. So you can see the problem with the type 2 error. You will see the problem with the type 2 error here. Okay, when x naught is not true, if x naught is not true, what is the, and then you decide not to reject it. This is a number that's often not easy or actually impossible to find unless you have some alternative hypothesis very specific. For instance, if you have your coin there, again, I'm not sure whether my coin has a probability of giving a head of 0.5 or 0.9. Okay, if it is either p equals 0.5 or p equals to 0.9, then it will be easier with our uh, critical region decided by alpha. We can see what sort of numbers, what sort of number of heads we get. We're not rejecting x naught. Then we can work out the probability that if x naught is actually not true, if p equals 0.9 instead of 0.5, what is the chance that we're doing this? Well, we'll have a wrong conclusion. Okay, but the problem is that if this is the main thing is, if we don't have a specific alternative hypothesis like p not equal to 0.5, you can see that whether p equals to 0.9 or p equals 0.52 will be very much different. If your coin has a probability of giving a head like 0.9, that means it's most likely to give you heads. So if you throw your coin like 100 times, you should see a lot of heads, a lot more heads than tails. Then that's no problem. Then you can see what is unlikely to be fair. But if the actual probability of getting a hit is like 0.52 instead, throwing your coin 100 times, you probably wouldn't see much difference. Okay, from what as if the coin is fair, like p equals to 0.5. That's the problem. So the probability of type. So when we say the beta, the probability of type 2 error, okay, fail and reject, so it kind of depends on what your alternative hypothesis is. Okay, could be large, could be small. You can imagine if p actually is 0.9, the probability of, so if you obtain like 12 heads from 20 throws, 12 heads from 20 throws, you wouldn't say that this is fair. Wouldn't say it is not fair or something. If your p is like 0.9, you should expect to see more, a lot more probably. But if you have p equals 0.52, you have less reason to believe that it should be the alternative hypothesis here. If you're getting 12 heads from 20 throws, okay, so that's the no problem. But you can see that, as we discussed the other day, if you try to reduce beta, you're most likely going to increase alpha at the same time. If you try to reject your x naught more often, then you're more likely to reject your x naught wrongly, and vice versa. So somehow we have to balance the two of them, if possible. Okay. So what exactly do we do? Other than our coins, I can test the frequencies or probabilities. Okay, test whether p equals 0.5. But yeah, we can do other sort of tests like the z test. Okay. Recall our central limit theorem, which says that no matter what population that we start with, no matter what population we start with, okay, eventually your sample mean x bar would behave like normal distribution, with a mean value, with an average value of mu and a variance value of sigma squared over n. Okay, so that you either have this or you may want to have this, so the z equals to if you change variables into z, so that it's x bar minus mu over sigma over square root of n, should behave like the standard normal distribution. The standard normal distribution, 0 mean, 1 for the variance. That is when n is large enough. 30 or 50 will do. Okay. You can notice this expression here. You will notice this expression here. The larger what happens with the size of z with the size of n. If you have a large sample size, you can see that this x bar minus mu over sigma. That square root of n there actually will go on top. If you understand the fractions of a fractions, okay, if you know how to if you understand the arithmetic of fractions on fractions, that square root of n is going on the top line. So if you have a larger value of n, you have a larger value of z. Remember, the larger value of these numbers, meaning it is a less likely event. Okay, so that is to say, if there is any, so if that is to say, if there's any difference between your sample mean and the true value that you're trying to test, okay, assume that you have a value, the mu in your mind, you want to check whether this mu equals to 50, for instance, okay, but you have your x bar equals to 51, okay, the difference will be 1, will be exactly 1, x bar and mu. If your mu is 50, you're testing it, you're trying to see if this is correct, if this is true, okay, and your x bar, your sample mean, turns out to be 51, the difference will be 1, but this is not enough for us. Is 1 large enough? Is 1 large enough? It depends on your sample size as well. If you have a small sample size, this little difference might be okay, comes from the errors. Okay, maybe it's not too large. Maybe it is something because x can be any numbers from this population, and if you have too few of them in your sample, it is likely that you have your x bar anyway. So with a large with a large error still. But on the other hand, if you have a square root, if you have n so large, okay, if you have n like 50, 100, 2000, so large a sample that any small difference between your x bar and mu will be magnified enormously because you multiply to this square root of n at the end. Okay, so there's because x bar should be very close to the true mean value, whatever that is, but yet there's a difference from what you are thinking. 50, you got 51, but you are thinking 50, but this 51 should be very close to the true value if your sample size is so large. So this little difference can mean that, which says actually there's something wrong with the mu there. Maybe the true value should be 50.8, maybe it's 51.2 instead, etc. The little difference will be magnified enormously. So there's a saying that the larger value of z, with larger value of n would mean you have a larger value of z, would mean that you're more likely to reject your null hypothesis. Okay. But the other thing to notice is in your calculation, when we say that x bar has a normal distribution like this, but you have z equals to these things here, but I've got a sigma on the bottom line. If there's no way we can tell mu precisely, if we're only testing an estimate of the mean value mu, if we're only testing like mu equals to 50 or something, not sure whether this is true, so we're testing it. How do we expect to know sigma? If we don't know mu, there's no reason why we should have sigma as well. Okay, that is the reason why we don't often have a z-test in your experiments. You're most likely be doing t-tests For those of you who know what it is, okay, doing with t distributions that we introduced earlier instead of z1, okay, because we don't have a large enough sample size, because we don't have a sigma value, the population standard deviation. We don't have that. We usually only have a sample standard deviation instead of a population one. Okay, in which case we're using our standard, our sample standard deviation instead S instead of sigma. Okay, but we're using our S instead of sigma. The thing is, if we have a large enough sample size, if we have a large enough sample size, just like before, we may say that our sample standard deviation should be a fairly good approximation to the true one. Okay, maybe we can say that what mu should be, but sorry, our sigma should be something like S. So we'll use this value, this sample standard deviation here. We'll just simply replace sigma, just use S over square root of n instead of sigma over square root of n. There's no way we can tell sigma anyway. So if we have a large enough sample size, maybe we'll just do S over square root of n anyway. Okay, instead. It's so useful that we're going to just give it a name like calling it the standard error from the mean, or SEM if you like. Standard error from the mean is S over square root of n, our sample standard deviation here. Okay. But that's but if you're using this, as many of us would do in our experiment, okay, we have to be careful between about the difference between the two. When we talked about the standard deviation, that is our S. Our SEM is our S over square root of n. Okay, the standard deviation S, the sample standard deviation S tells you what happened to your data values x1, x2, x3, how far away they are from each other. Okay, tells you how far away they are spreading. Okay, that you have got your 100 numbers for your data from the sample. So if you have a sample size of 100, it tells you the spread of your data, how far away they're going from it. So because each of the x's, they come randomly. They can be anything. So this S doesn't really change. This S doesn't really change if you have a larger or smaller sample size. It just tells you how far they are away. So these things can be anywhere after all. But SEM is different. SEM is different. It tells you if SEM does decrease with n. This SEM thing here, it has no actual physical meaning. It doesn't have actual physical meaning, not like your standard deviation that tells you how the spread of your data. But this SEM thing, it only tells you how accurate your X bar is from the true one, and how good your estimate this X bar is. The larger value the larger value of your sample size, the smaller value of your SEM, this standard error, it means that your X bar is closer, or should be closer from the true mean value. Okay, that means even though we could still have the same sample size, and then we have similar sample mean there. Having different sample sizes, having standard deviation, we can have this a rather large standard deviation. We can have a rather large standard deviation, meaning all the x's can be everywhere, but a very small value for the SEM if the n is large enough, meaning that our sample mean, even though x's are everywhere, even though x's can be large, can be small, but x bar is close to the true mean value. Okay, so just that means some of them will be too large, some of them will be too small, then the effect of them will be just cancel out, will be just cancel. Okay, so you still have the sample mean very close to the true mean value, even though the spread of all x's could be large. Okay? The difference between the two is this. It's very subtle, and for people often confuse between the two of them, especially if you see experiment reports, or maybe even you write your experiment report, you give your data, you work out your mean value, you would write down your standard deviation as well. Some people confuses the standard deviation and the NCM. It use the two of them interchangeably, but you can't because you can see there's a factor of square root of m here involved. So you can't just use any one you like, and it could be confusing, and even sometimes this confusion is intended to be there, just to confuse the reader. Right, also, sorry. So be careful about the use of these things in your own experiment report and when you read other people's reports. But then, well, okay, later we'll do a bit more about this hypothesis testings, trying to test other things. But here's the thing: if you think about that, if we could, like, hypothesis testing is like having a mu value. I have a value, the mu like equals to 50. I would like to test if this is true, whether mu equals to 50 or mu greater than 50, for instance. Okay, I don't know what mu is, but I just have a number in our mind, and then we use our x bar to see x bar value, using the alpha value to see whether this is likely to be true. Can we do the opposite? Can we do the opposite? Like, I do my experiment first. I have my x bar, and I use my x bar and guess where the mu is going to be. Okay. After all, if my sample size is large enough, x bar should be fairly close to the true mean value mu. Then why don't we just do the experiment first, having our x bar, and then we say, well, it is likely, it is so much likely that the true mean value would be somewhere in between, rather than to have a guess, to have guessed a value of mu before our experiment. We can actually do that. This is what we call the confidence interval. We can do it either way. Okay, we can do these things either way. We're having a confidence interval here. This is exactly what I was saying. You can do an experiment. We have our x bar. Then we say that there's a range of values. There's an interval in which the true mean value mu should fall within. Okay. So especially if you have no idea where that true value should be, so you're not even testing for this thing. You just don't even have an idea. Maybe I'll just go along and do an experiment first, and say that if I have a large enough sample size, for instance, then we say that we are 95% confident. We're 95% confident saying that mu belongs to this range. Okay. Again, 5 is like the opposite of your 5% significance level here. It doesn't have to be 95%. It could be other numbers. Okay. But why 95%? We want to be fairly confident. We want to be fairly confident to say that mu is somewhere close to your x bar, somewhere near your x bar, but we have to write down an interval where mu should be. And if you have a large range, then it's more likely this is true. So you're more confident to say that mu will fall in this interval. But if you have a small range instead, there's a very narrow gap there. It means, well, your mu will be less likely to be in there. So why don't we just have a very wide range? Why don't we have just write down a very wide range, like in this example here, like in this example, imipramine, okay, and imipramine. I'm sorry, I don't know much about drugs. This is as I check that is as I check this is some kind of antidepressant, okay. So these people take these drugs for these pills for when they have depression and all that. But here's the thing: suppose that okay, they want to check out the amount, the actual imipramine amount in these tablets. Okay, they've done an experiment. They've got 9 of those numbers. Of course, in reality, you may want to have more, but suppose that you've got only 9 of them. And of course, they're not going to be all the same. The amount of the content would not be exactly the same for all of them. So you can see from the table on the left, you get all sorts of numbers. And on the bottom, you can see the mean, plus or minus. I've got this is the convention. They have the mean value, and they have the plus or minus, the standard deviation value. For some reason, they put plus or minus. I don't know why, but this is the standard deviation value coming up. And then you can see that you've also got the SEF value is the standard deviation value divided by square root of n. You've got 9 of these numbers, so the sample size is 9. Square root of 9 is 3, so you 0.81 divided by 3, you've got 0.27. Okay, so you've got the mean, you've got your standard deviation and all that. So 25 point something plus or minus or whatever standard deviation you have there. What does that mean? What does that mean? If you want to be really confident, okay, if you want to be really confident about our true mean value, I remember I don't know what that is. I'm just saying that it is likely to be near this sample mean 25.32. Okay, how likely is it? I can be very confident and say it's going to be 99% or even 100%. Well, I shouldn't say 100%, 99.999% confident to say that the true mean value should be between 0 and 50. Yeah, if the sample mean value is 25.32, if all the numbers that you're seeing it goes from 24.7, 25.8, 26.7 and all that, I think I'm definitely not going to get this wrong if I say the true mean value should be between 0 and 50. I'm very confident. I'm most likely to be right. But would you say this is a nonsense? But would you say it is useless? Not informative. Okay, I can have a really large range here. I just write down a large range here for this confidence interval. I'm very confident to have our true mean value between these two numbers. Good, confident, but maybe less useful. On the other hand, if I've got a very narrow gap, if I've got a narrow gap here, I've got very small range instead. Yeah, if this is true, that if the mean value actually falls in this gap there, it will be good because I've got a very accurate number. Okay, I've got accuracy, but I have to lose my confidence. I've got a small range here. That means it's just less likely that the mean value would really be there. Okay, in this case, I would have to say I'm only 90% confident or 85% confident instead. Okay, so to have a compromise of the two, so we normally take again 95 here. Let's the compromise the two. I'm having the 95%. Saying that is we're 95% confident that the true mean value should fall within here. Okay, we could say 99. We just have a larger range. That's all. If you're doing something very, you want something really uh, accurate, then of course you will have to increase your confidence. Okay, making sure that that you really get to the true mean value. Okay, then you have 90%, 99%, or 99.9%, etc. Okay. So the confidence interval is just as easy to calculate. Confidence interval is just as easy to calculate. Again, if we do our normal distribution, if you remember that our normal distribution, we talked about the mean value, and then we talked about our bell shape, and we say that if we move away one standard deviation, which is mu plus sigma, mu minus sigma, this should cover about 68 to 70% of the data. If you go all the way to 2 standard deviations, they need to go to a bit more than 95%. Okay, it'll be a bit more than 95%. So that's what we do here. To have our sample, this time we're having our sample mean. We're having our sample mean here in the middle. Because we're assuming our normal distribution here, if we have a sample size large enough, our x bar would look like a normal distribution. So when we have an x bar value, we can say that, well, this range, this confidence interval is given by x bar plus or minus two of them, almost two of those SEM, this standard deviation here, s over square root of n. S over square root of n, that is the standard deviation for the distribution of x bar. The standard deviation for the distribution of your sample mean there. Okay. In fact, you can just look up these numbers from these tables or whatever it is, or simply remember them. 1.96, almost 2. If you want 95%, you need almost 2 standard deviations away. Okay? If you have exactly 2 standard deviations, it will be slightly more than 95% here, as we saw from the other picture that we have. Okay, so that we have our 95% confidence interval. Okay. So in this particular example, we've got our sample mean there. We can have our SEM value given already in the table here, 0.27. You just multiply to 1.96 and then add or taken away from your sample mean. Then you have your interval where the true mean value should fall within, well, with a confidence of 95%. If you prefer 99 instead, if you prefer 99% confidence interval, of course you can just look up another value from the normal distribution table. In this case, you have 2.58. Okay, in this case you have 2.58. That means if you go 2.58 of the standard deviations away from the left and the right, you're covering 99% of all the data. You're covering 99% of the chance that the true mean value should be in there. Okay, that is when you when you don't have much idea about what sort of values your true mean value should be. Then you do a confidence interval. But of course, there's nothing wrong with the hypothesis test like before. So if you are testing your whatever, so surely this content from this tablet, you just check out the box. It should say the content should be, well, on average like 25 or something. then just test using this experiment result checking whether this value 25.0 given by in the box is accurate, then it'll be the same. Yeah, performing one of those Z tests or T tests. Okay. If I may give you an example here, to see if you understand these concepts. Okay, suppose that we've got hospital, we have our emergency room. The problem with emergency room, well, anywhere in the world, I suppose, is that people will have to wait for too long in an emergency room. Okay, you want emergency service from a hospital, but when you actually get to the hospital, you don't get to see the doctor immediately. Well, unless you have some really serious problem. You see, in an emergency room these days, they usually have there's usually a nurse coming here to check what you've got, ask you what you have, what your problem is, and then if you have more serious problem, then you get to see the doctor first. If you've got something very minor, then you just have to wait to be served. Okay. The problem with emergency room service is that people normally have to wait for too long. Okay. Nothing like emergency really. If people have to wait for too long, so suppose that this hospital here wishes to improve the service, so they want to reduce the amount of time people have waiting. So in their study, they first checked how much time people would have to wait normally or on average. So they asked their patients, okay, again, a simple random sample of 64 patients here. Random sample, 64 patients. What does that mean? That means they're asking their patients how long they've been waiting, how long they've waited in the emergency room to be served. But again, what do we mean by why do we mean a random sample? Of course, you don't want to get all your 64 patients all at the same time of the day in the week. In the week, you may want to try different days. Maybe weekend we've got more accidents, maybe due to the parties and the weekend and all the things. Maybe we have got all the we've got more accidents or more emergency service required, like in the night instead of in the daytime. There's a random sample. We want to pick your samples like randomly, so to be fair, so that you have some fairness in your statistics. You don't want to just pick a quiet time in the day and then in the week, so that you have a different values. Okay, suppose that we're collecting this sample randomly. We've got 64 of them, and suppose that we give them questionnaires or simply just ask them questions how much time they have to wait until they were served. Okay, suppose that they've got some sample mean value and whatever, and therefore suppose that they've got a 95% confidence interval. They've got a 95% confidence interval. Given us this 128 minutes to 147 minutes, that is 2 to 2.5 hours. 2 to 2.5 hours. Okay, assuming we've got normal distribution and all that, blah blah blah, etc. I've got false statements coming along, and you have to tell me which one are false. Sorry, I've forgotten we're doing this class online recorded, so you're not answering my question. I'll have to answer this myself. Okay, I've got 4 of them there, but you have to think about that. You have to think about them together with me. Okay, I've got a confidence interval of 95% here. This 128, 147, whatever. Then you say this confidence interval is not valid, since we do not know if the population distribution of the ER wait time is nearly normal. Okay, the confidence interval is not valid. There's no point in doing this confidence interval after all, because there's no we don't know anything about the probability distribution of this waiting time. Okay, is that true? Is that not true? This is actually not true. This statement is actually not true. Yes, that is right. We do not know. We do not know the probability distribution for the population. We do not know the probability distribution for the population of this waiting time. It's actually most likely going to be exponential distribution. But anyway, we don't know what probability distribution this is, but it doesn't matter. It does not matter. Okay, the whole point about this central limit theorem and this confidence interval thing is that we don't know what x is, what probability distribution of x, but we do know what the probability distribution of x bar. Okay, the sample mean, we do know the probability distribution. It is going to be normal, based on normal model of the mean. The x bar is roughly normally distributed, and therefore why we're having our confidence interval written down like this. It's nothing to, well, it's nothing much to do with the actual probability distribution for the population. Okay, so the confidence interval is of course valid, whether or not we know about the population distribution. Okay. Second thing, or the second statement here was, we're 95% confident. We're 95% confident that the average waiting time of these 64 patients involved in this questionnaires, in this experiment here, we're 95% confident that the average waiting time of these 64 emergency room patients is between 128 to 147. Okay, is that true? Is that not true? Again, this is not true. This is not true. This is false. We are not 95% confident. We're not 95% confident. We are 100% confident. We are 100% confident that this average waiting time of these 64 people, okay, the confidence interval is about the true population mean here. And and this interval is given by our sample mean, our mean, our average value for this sample. Okay, so I can say definitely the sample mean value, the average waiting time of these 64 people, that is our sample mean, is right there, probably most likely right there in the middle of this interval. Okay. We're not just 95% confident, we're 100% confident that X bar is right there in this interval here. Most likely right there in the middle, exactly middle. Okay, what we are 95% confident is, well, the third statement here. What we are 95% confident is that the average, okay, the mean value of all patients, okay, the ones that we don't get to ask, okay, all of the people here, on average, the true mean value is between these two numbers. We're 95% confident that we have these true mean value between these two true mean value between these two numbers. Okay, that's the point of our confidence interval. Okay, it's not that where we are confident that our sample mean is between the two numbers. We have our sample mean, and then we have our interval here set up. Okay, so if the sample ought to be right there in the middle of this interval here. The last statement, however, is the one that people often, don't understand, or people will often get this wrong. Yes, we always know that increasing our sample size will make things better. We always we know that if we want to reduce any errors, we will increase our sample size. We're less likely to make errors. We're having more accurate results and all that. So if we want to have So if we're having a confidence interval with 95%, that means we're still possible to make errors. We still have with this interval here, we're still having 5% of chance of getting this wrong. There's 5% of chance that mu is outside this interval. Okay, so suppose I would like to have the interval, well, to a better accuracy. Okay, I would like to have a 95% again 95% confident that with a narrow, with a smaller gap, with a smaller interval here instead of this one. We would increase our sample size. Would like to see if we increase our sample size, would make this confidence interval like narrower. 95% confidence it will be well within a smaller range. If we increase the sample size, most likely, yeah, this is probably going to be the case. More likely for the true mean value to be within a smaller interval. That's fine. That is fine. But what people they often get this wrong is if you want to make this like twice as accurate, I don't know. It says the decrease the margin of error to half or what it is, but so, I mean just twice as accurate if you like. We double the sample size. Okay, this is not necessarily true. This is not necessarily true. We know that if we double it, if we have our sample size increased, we have the error reduced. But it doesn't necessarily come in that particular relation. If you double it, it will half as much. You see, we have got all these normal distribution function, like the exponential function. Remember, we've got all the square root sign of n there, square root of n for the for sample size. This I don't know why people think that, but there's no reason why these things should be directly proportional to this. So if you double the size, then you have half the error. It doesn't work like that. Okay, it doesn't work like that. But we do know the general idea is true. If you increase the sample size, we're going to reduce the margin of error, but not exactly in that sort of way. Yeah. So if you imagine you have a sample size from 30 increased to 60, then you probably will have more improvement than if you started with 3,000 and then go to 6,000. Because 3,000 is already very good. Your error is going to be very small anyway. You increasing that to 6,000. It may not reduce that by as much as well, like when you increase from 30 to 60. So it comes to it leads to another issue of yes, we know that increasing our sample size would make things better, but in reality, when we are performing our own experiment, we have to think about the cost, the resources that we have, and also the things we can't increase our sample size unlimitedly. Okay, we just can't. We just have keep increasing our sample size. Unless you've got a lot of money, time, and all that to repeat experiments as many times as you wish. And after all, even if you could repeat your experiments that many times, again we have to think about the effect. Are we getting much improvement anymore? There will be a point. It will come to a point that increasing the sample size would have not much effect anymore. Not worth the effort of increasing this anymore. So that's where we will stop. Okay. In principle, mathematically, if we allow n to go to infinity, then good, then of course. But in reality, no, we're not going to infinity. We're not going to have our sample size enormous. Okay. So let's just consider an example here. Suppose that we've got a machine where a manufacturer here. Suppose that we've got a certain machine that makes electrical resistors. Electrical resistors. I don't know if any of you are familiar with these electronics, or when you did your physics class in school, that you have all these symbols. So for the battery, for the bulb, and then in this case we have electrical resistors. Suppose you're making electrical resistors having a resistance of 40 ohms, 40 ohms, and standard deviation of 2 ohms. Suppose that this is the claim from the manufacturer. We're producing these resistors with 40 ohms each. But of course, these things will come with error. So there's a standard deviation of 2 ohms. Okay, suppose that you would like to check. Suppose that you would like to check whether this is true. Okay, so you get a sample of 36 resistors. Maybe you're just an outside institute wanting to check whether this thing is good, or you simply a quality controls section from the company. Okay, the manufacturer wants to check whether they're producing things precisely what they want. Okay, so they collect a random sample of 36 resistors. Again, random sample. You don't want to collect your resistors from the same box, basically. Okay, you want to pick them randomly from from different from different production lines, or from different people, maybe different days in the week. Like if these things we have to go through human hands, and you know that they're having more skillful workers or less skillful workers, maybe there's a difference, etc. So we want to collect these things randomly. So you just open a number of boxes, and then you just collect the resistors, all of them, 36 of them. Okay, suppose that you have them resistors. What do? You check out the resistance for each of them, and check out the resistance for each of them, and then find the sample mean, find the standard deviation and all that, etc. But if I ask you, how would you do that? How would you do this experiment? You get all these 36 resistors. How do you check their resistance? How do you check this? So, so if you got one of those electrical resistors, I don't know if you still remember your electronics from school. That's your battery. Okay, honestly, I don't know much about physics and electronics, so that's all I have. So suppose that you have your thing here. How do you check the resistance of? You've got your ammeter, and you've got your voltmeter. Okay. Then your Ohm's law says that the resistance is simply the voltage divided by the, sorry, not a current. Okay, the resistance of whatever you have there is given by the voltage divided by the current. Okay, so that you just connect these guys to your ammeter, so that you have your current done, and then you've got the voltage from the voltmeter. Then you can just divide the two, then you get your resistance for each one of them. But the thing is, many of you, I don't know if you all do experiments, okay, or any kind of experiment. I mean, you do experiments, you know that any measurements that we have contains errors. If we have each measurement that we do, we have errors. So if we do, I've got 36 of these resistors. If we check the resistance for each one of them by connecting them to one of these ammeter and voltmeter, so we're getting an error from here, and we're getting an error from there. Therefore, each one of them will have a error in the resistance that I obtain. Okay, but I've got 36 of them. I've got 36 of them. What would be the error when I have to work out the sample mean of them. I have to add the whole lot together, divide by n, remember? I have to add all the resistance together and then divide by n. So I have to include a lot of errors in here. So this is not necessarily the best way to do it. So you notice from my question, it says a random sample of 36 resistors has a combined resistance of 1458 ohms. What's actually happening is, instead of finding the resistance for one of them, we're finding the resistance for the whole lot of them. We just connect all of them together in series, and we have our voltmeter. Sorry, and we have our voltmeter connected like this. We find out the total of this resistance. Okay, so we check, because we know that the total resistance is given if you connect all of them in series. If we could connect all of them in series, then we just need to add up all the probability, all the resistance together. Okay, in which case we only need to do two measurements, one from here, one from here, instead of 72 readings. Okay, we're checking this, but we're having two measurements only. One current, one for voltage, and then we just divide the two using the Ohm's law, and we get the total resistance of the lot. After all, we're just adding them together. I don't care what they have for each one of them. Yeah, so this might be better. So we have a combined resistance of the lot 1458, so that I only need to divide by 36 to obtain my sample mean there. Add them all up, divide by n, so I just take this total to divide by 36. I've got 40.5. This would be my sample mean. Then my question is 40.5 different from 40? Is 40.5 different from 40? I'm checking whether the true mean value, whether the true mean value should be 40. But my experiment results gives me 40.5. What does that mean? Is it too different from 40? Is 40.5 too large? Okay, that's what we are doing here, having a hypothesis test here. Okay, checking whether mu is 40 or not equal to 40 with a 5% significance level. Okay, so we can write down our null hypothesis, the one with the equal sign, mu equal to 40 or mu not equal to 40 as an alternative hypothesis. That means if you have your sample mean very different from 40, so presumably if you have x bar like equal to 50 instead of 40.5, then you would probably say that your null hypothesis is going to be rejected. But 40.5, is it too different? Maybe it's not. Maybe it is. I don't know. It depends what? Depends on the sample size as well. It depends on the sample size as well. If you have only two resistors, if you've only got two resistors, I would probably say 40.5 is not too bad. But if you have got 200 resistors, 40.5 probably is a bit different from 40, because I've got 200 of them. This 40.5 should be fairly close to the true one. And 40, well, it's the little difference of 0.5 is a bit too large if you have a sample size of that many. Would you think? Okay, so these things depends on the sample size as well. So what do we do here? Have I got I've got them. I use our central limit theorem again because I've got my sample of 36 resistors. I've got a sample large enough, and I'm also using this as my sigma value. I'm taking I'm taking this number from the manufacturer's claim, this as my sigma value. I'm testing whether this 40 is true, is accurate. So I'm taking this as my sigma. I have my sigma, so I'll be using my central limit theorem where my sample size is large enough. That means what? That means with a 5% significance level, with a 5% significance level, I want 2.5% this way. With a 2.5% this way. A 5% significance level, that means this is I've got a two-tail test. And therefore, I need to divide so I need to have my critical region in two bits. One of them being too large and one of them being too small. After all, you don't want your resistance to be too large or too small from 40. That means I can just look up these numbers from my table, 1.96, meaning that the probability of getting more than 1.96 is 2.5%, just like the one before, that we have our confidence interval. When we have a confidence interval before 95%, that means 2.5% one side and 2.5% the other side. Okay? Or alpha over 2. Okay? And sorry, this should be a mu there. And I just need to see if my sample mean value would be large enough, would give me a z value large enough. In this case, just work out 1.5. 1.5 is here, not too large, not so large that belongs to the critical region. Therefore, we cannot reject our null hypothesis. Okay, we are not rejecting our null hypothesis because of that. Okay. Maybe you can argue, okay, if we continue with our experiment, if we have 100 instead of 36, maybe we'll get a bit more reliable results than 36. Especially if we're still getting 40.5 for our average. Okay. But here's the procedure really. You have to write down your hypotheses. Then you have to understand what test we're doing here, a Z test or a T test or whatever, and we know that it's a two-tail test, so that our alpha has to be split into 2.5s and 2.5s. Then we just look up the critical values from these tables, and at the end we perform our experiment, get our 40.5, and then we use when we check out our X bar and see if this belongs to the critical region, and that's all. Okay. Another example. Here's one that is a one-tail test. Suppose that a doctor claims that the teenagers may have higher body temperature than normal people. I don't know if this is true, but suppose that this is what a doctor believes. Okay, he wants to perform an experiment to check whether this is the case. So again, he collects a random sample of a number of people. I've got 25 here. Again, 25 because I've got square root of n. So I've got a bunch of people here checking out the temperature, body temperature, 37.2. Again, well, it looks like we've got slightly higher than normal, 37.2 instead of 37, but I've only got a sample size of 25. Is that good enough? Suppose that the true population is something like normal with a standard deviation of 0.4. Suppose that I've got a true population that gives standard deviation of 0.4. That is your sigma. Then can we test this 37 degree, can we test this 37 degrees? Can we test this hypothesis here? Test whether mu is really equal to 37 or more than 37. Yeah, because the doctor claims that these things will have a body temperature higher than 37. Then if you're getting something lower than 37, if your sample mean turns out to be like 35 or 36.6, we wouldn't say it's higher. We still, of course, we're going to still keep our null hypothesis. In this case, we have a one-tail test. We have a one-tail test. That means we have a normal distribution table. We look up for values that gives us 1% precisely. Okay, we don't have to care about the things on the left. Okay, this is the one-tail test. We look up the value, critical value here from our normal distribution table. In this case, 2.33. 2.33. Okay, that means 99% is going to the left and 1% towards the right. So the critical region is given by z greater than 2.33. Then all we need to do is take our x bar and see if we can work out a value of z bigger than or less than 2.33. In this case, yes, it's bigger than that. So we're rejecting our h0 and saying that our null hypothesis is likely to be not true. That is, mu is probably greater than 37. Again, with certain probabilities here. It's likely to be greater than 37 instead of exactly 37. Yeah? Does that make sense? Does that make sense? Okay. Does that make sense? We know at the end of a hypothesis test, we're just comparing numbers. We just work out whatever we have for the z value, what that equals to 2.5, and then we just compare that with our critical value. Greater than, then we reject h0. If it's less than, like the one we had before, 1.5 against 1.96, we just do not reject h0. That's all. At the end, we're just comparing numbers. We just need to look up the critical values from whatever tables we have from Excel, we have, or etc., using the value of alpha. And then we take our x bar with whatever experiment results that we have, work out the statistics that we use here, z here, or t, as we shall see next time, and see which one is bigger. That's all. But sometimes you may wonder what's the actual probability of having such an event. Okay, we say that z is 2.5, so it's greater than 2.33, therefore we reject h0. That means it is an event that is 2.5 is here. That means it's going to be an event unlikely to occur with a probability even less than 1%. But how much? If less than 1%, but exactly how much? Sometimes people like to quote these probability values. We can do that. We can actually have this probabilities. That, of course, we have talked about the normal distributions and all that. We have seen this table, worked with these tables before. If we have a value of z equals 2.5, we can simply look up the probabilities from there and see that the probability of z greater than 2.5, so unlikely. This is an event so unlikely to happen. How unlikely is it? It is about 0.6%. 0.6%. Well, smaller than 1%. Therefore, we are rejecting a null hypothesis. Sometimes people prefer to see this thing in actual numbers than simply comparing with the critical value. Okay. And the previous one, especially the one that we had previously, the one that we had at z equals to 1.5, it is not in our critical region of 1.96. Okay, but we may but we may still want to know the probability of it. How likely or how it is not unlikely enough, but how likely is it to occur? Remember, we are having a two-tailed test. That means if it is too large or if it is too small, it is no good. So we're having z greater than 1.5 or less than minus 1.5 to consider, to have the probabilities add together. Turns out to be greater than 13%. 13%, is it really high? It is not really very high, but it's a lot more than we can tolerate. A lot more than we can tolerate. Okay? It is an event that is not so unlikely to occur, and therefore we cannot reject our null hypothesis just like that. Okay? It's not something very impossible to happen if we assume a null hypothesis to be correct. Okay? I hope that makes sense. Yeah? That's the bit about the idea about our hypothesis tests. Okay? In a bit we're going to check out other hypothesis tests like the t-test. Okay?